periodic function. Okay. And another definition is arc function. Arc function is if we replace x by the negative x. So this is the x. By the negative x, that is, we are moving from this direction. We have negative value. So we have positive value here. We have negative value here. We call this function as what? It's an arc function. This is easy for you, right? You knew this already. And if we replace the x by negative x, you are going to have same function value. So this is your fx. If you move toward the negative x direction, you will have same function value. Then we call this function to be the even function. Okay, I think this is very basic for you. Okay. And let's look at this part. Say for any function fx, if we add this term at over 2 and subtract this term over 2, so these two terms can be cancelled by each other, right? So we are doing nothing. But once you have done this, if we call this the first part to be the, we call this to be the h function, we call the second part to be the g function. And can you see that h function is what? It's an even function. And the arc function is what? It's an arc function. That is, any function fx, it can be decomposed into even parts and odd parts. For instance, if this function goes to 0, then the f function is an even function. If this goes to 0, this part, then the f function is in what? It's an odd function. It can, anyway, for any fx, it can be decomposed to parts. And say for the even part or the odd part, it will vanish for some reason. Then the result term will be what? Say for this one, if we don't have an odd part, then this function will be an even function. Okay? Then let's look back. According to Fourier's observation, so if you can see, cosine x is what? Is an even function. And sine x is what? Is an odd function. Any function can be decomposed into, say, the pink color or the purple color. This part is what? Even part. And this part is what? Odd part. It can be separated into parts. That's why when you wish to use sinusoidal to simulate a function fx, it requires two parts. And if the fx is an even function, then all the bn equal to 0, such that this part vanished. Agree? And if this fx is an odd function, then this term equal to 0, and all the coefficients here equal to 0, such that this term vanished. So you have a odd function. Okay, depending on the nature of the function, it will, of course, this will determine your an and the bn. So the colors, so I use different color to represent even, and the blue color to represent odd function. Okay? Okay, then let's start to find or to determine the coefficient. And based on the formula I just showed you, the coefficient will be determined by f times the sine, either sine or cosine here. And here we have the sine nx known to the square, okay? So we go back to here. And before we conduct, since we know we are going to times fx, say let's take cosine nx for instance. So it will equal to a0. Fx is the expansion of this one, right? So you expand, replace f by the cosine series. Okay? So you have a coefficient here. Okay? Then let's go on. And before we proceed this, I just provide you some very important yet useful formula here. This is regarding the integration of the cosine itself, and this is the integration of cosine, cosine, sine, sine, and cosine, sine. Okay. I hope there's no typo here, but it will be very nice of you to check do we have any typo here. If we do have typo, please let me know. Okay. But anyway, let's go back to here. So the expansion of the cosine series will be something like this one. And so here we can substitute this one directly by the formula we have. Here we just times cosine for each term. We use another approach. But anyway, you can find using the formula here, you can get this coefficient directly. So you have a0, this is even function by the way, it's a constant, and an, this is the coefficient for the even function, okay? So it's say an basically is the product of fx with the cosine nx, and integration for the time being, the range is from minus pi to pi, okay? So we consider from negative pi to positive pi, the range, this range, okay? And likewise, using the same formula, you can determine the coefficient for the arc function, okay? So this is the summary. But here, we just to use a series expansion of sinusoidal function to represent fx from negative pi. So far, the range we are talking about is the x, okay? But fx, of course, is not necessarily a periodic function. For instance, this is your x, this is your y, or your fx. Say this is your fx between negative pi and between positive pi. And actually, the function could be something like this one. It's not necessary, fx itself is not necessarily a periodic function. But our purpose, say for the given a and bn, we just simulate the fx from here to here. And we do not consider anything of the x outside this range, okay? So as I just mentioned, we should pay attention to this series expansion, okay? And should we have a look at one of the example? Yes, not this one. Say, we have example 8.2. Say, this is the definition of fx, so the range here we have is minus pi here. We have positive pi here. So according to here, this is the graph of the fx during the range you want to simulate. So you just follow the formula. You can determine your a0. So your a0 is this one. After the integration, you can find use the same formula for your an, and use the same formula you can find your bn, okay? So here, I just show you the result. So if this is your f function, as I just mentioned, so during the negative pi and positive pi, the green line represent, say, if we consider n only up to 2 only, and this is the outcome of Fourier series expansion, quite close to this function already. So if n here, n equal to, for A, that is, we use A0, A1, A2, and B1, B2. Okay, so this is indicated by the blue line. And for this case, we use A0, A1 up to A6, and B1 up to B6. So we use more terms to represent the result. And well, it's even more close to the actual fx function. But we can see we have some change. Say the function here, we have a discontinuity point here. Or we have sharp edge here. We have edge here, we have edge here. And from this point on, we do not have edge. So this, the blue line indicates the result of Fourier series expansion. The more term you get, the first result is the more term involved in the Fourier series, the result you get is quite more closer to the actual fx during the range. This is the first thing. And the second thing is when fx has an edge here,